Wow. Very expensive.
Okay. Yeah. I share my screen and I think I'm good to go. All right. So
You want to make that full screen?
okay.
Yeah.
Okay,
so,
let me put it right here.
Yeah, so very quickly again, the format is going to be Hanfeng will give a talk for about 45 to 50 minutes. And then we'll have about 15 to 10 minutes of Q&A from the audience, and then we'll interview banks, Jasmine and Derek. You know, giving a hard time basically. So, so yeah,
I'm excited for it. Okay. Oops, let me remove that sign. Okay. All right, great. So before I begin, it's very excited to be here, and I'm very flattered to briefly summarize some of the work I've done in the past 18-20 months and highlight some of the results only briefly. And also, it's very lucky to have JJ and Derek on my committee. So let's begin. My name is Hanfeng Zhai, and today my topic is going to be multi-scale modeling and machine learning design optimization of nanomaterials sustainability, where the toolbox we use is modeling and optimization, and our target is nanomaterials and to focus on applications in energy, biomedical, a lot of different kind of application side. Oops. Okay. So let's begin with a very simple motivation or a question is, what are good materials? Well, academically or rigorously, we don't seem to have a very academically rigorously definition of good, because it's a very subject term, and a good material can be a lot of different kinds of material. It can be something very high strength, high stiffness, very hard like diamond. It can also be soft, bioadaptable like spiderweb. So about all these kind of different materials have all these kind of different fancy properties. They all have like the definition of good is based on your application, and you have some desired properties, and as long as the material that fits your desired properties, we can consider it as good. But also different materials have different properties. They all preserve the intrinsic relationship, where you have different structures on the multiple scales, like multi-scale structures, and they have, based on the structure, they have their corresponding properties. And this structure to property map is intrinsic of the relationship of all these different kind of materials can be represented by a very simple mathematical formula or a pseudo formula, which is you have some X as a structure, and then you have your corresponding property Y, and this X to Y map can be represented in the model. And in my research, this X to Y map is achieved through one thing, it's called computations. All right. So let's follow up on the previous question. Is we know there are no universal definition of a good material, then we would like to ask a follow-up question is, how do we understand and design good materials? So to answer this question, we should think of this question from two aspects. We'll break it up into two sub-questions. First is, how do we understand good materials? The other is, how do we design good materials? So to understand good materials, our proposed solution is to use multi-scale computational modeling, which is you have a lot of different computational models on different scales, spans from ab initio scale to molecular scale to the continuum scale, and use those computational models to explore this intrinsic relationship and to kind of explain some mechanism we observed in the materials and their corresponding properties. And this is how we understand the good materials. And how do we design good materials? As I mentioned in the first slide, is we don't identify a universal definition of a good, but as long as it meet your applications and your corresponding desired properties, we can consider them as good. Then how do we design? Is you need to have your application first, and you have your desired corresponding property, and then you first tailor the structure of the material to obtain your corresponding desired properties. So now we think back from the very first slide, I have this very simple X to Y map. How do we apply that in the schematics? Well, if we look at multi-scale modeling and we think of the schematic, in the molecular scale, you can have this X to Y map. And in the ab initio scale, you can also have this X to Y map. And in a continuum scale, you can also do this XY map. But believe it or not, many decades of development in computational modeling and a lot of researchers doing effort in this field, we can achieve very high accuracy for ad hoc scale model. For example, in a continuum scale, like spectrum element model can achieve super high accuracy. And in the molecular scale, well, if you use reactive force field to compute specific property of interest, like combustion work, you can achieve also very high accuracy based on a specific tailored problems of interest. But what I am personally fundamentally interested in multi-scale modeling is we have all those different XY maps. how do we start to explore the relationship between those ad hoc scale models and to start blurring the boundary and make some connections between those scale models, or even at least trying to understand the different relationship between the scales. And that will be the first part of my talk today. And if we look at how do we design good materials, we can also identify the multi-scale modeling map in general, like molecular scale in red, a mesoscale in green, and a continuum scale in blue. Then you can also apply the XY map for different scales. For example, you can do that in the mesoscale, in the molecular scale. But if you want to do design, you have to have the application like cars, airplanes, and batteries. Then you know your Y initially. You don't know your structure of materials, but you want to tailor it. You want to obtain the corresponding X. So how do we do that? In this one, we do inverse design that you inversely get the corresponding structure of material. And this is the overall general layout of my talk today. This is going to be the first part 1, and this is going to be part 2 and part 3. Okay, so let's begin with a very fancy, a lot of schematic, very simple material. It's called graphene, and we name it a wonder material. So what is graphene in essence? Graphene is basically a single layer of carbon atoms displayed in a hexagonal shape that has exceptional mechanical, thermal, electrical, optical, all kinds of fancy properties. And also won the Nobel Prize in Physics in 2010, we have mentioned. But what is initially drive me interest in graphene is not those like fancy applications and properties. What I'm essentially interested about graphene is because it drives so much attention, so many researchers study this material. We have those different computational models for graphene. We have ab initio model, molecule model, and continuum model. So what I'm interested in essence is how do we start to explore the relationship between different computational model for ad hoc scales and start to make some connections and learning some new stuff by investigating the relationship between different scale computational models. So then we want to do some research about graphene. And if we want to do a research, we need to begin by asking some questions, interesting questions. And at least I believe a good research begins by asking a good series of questions. So what question did I ask about graphene? The first question I asked is, what's the effect of empirical interatomic potential in modeling computation? Why do I ask this question? Because for decades, so many researchers study graphene, not a decade probably. So many researchers study this material, and a lot of even like the most big shot professors like to take assumption that, well, this specific ad hoc model is very accurate in predicting this kind of property, like say mechanical properties, and we kind of assume that this model is accurate, and then we start exploring using this model and to match this experiment and propose some mechanism of graphene. But then we have all those different empirical interatomic potentials for graphene. Then the question I'm curious about is, all those different models can predict pretty good accuracy for different properties. What's the relationship? Well, can we benchmark and characterize different empirical interatomic potentials for graphene? That's driving me to ask question number 1. And what's the question number 2 is, can we benchmark empirical potential with machine learning potential? And why I asked this question is in the recent 2 or at most 5 years, there's a exponential growth in the machine learning potential. It's basically the idea is you train a neural network, or it can be Gaussian process or any regression model based on your ab initio calculation data, and then you generate a map between a coordinate, or it can be a symmetric function I will mention later, to the energy, and you apply this target model of the energy to the molecular simulation. And then you can actually conduct the molecular dynamic simulation. But how does actually trained machine learning model that propose to bridge the scale between ab initio and molecular, that propose to scaling up the ab initio high fidelity calculation actually performed in a molecular scale? We're curious about that. That's why we asked question number 2. And what's the question number 3 is, because of the mechanics background, so can we verify molecular dynamic simulation from mechanics theory or general mechanics? This is not a strictly continuum mechanics, and I will elaborate later, but can we kind of make some connection between the field I'm familiar from mechanics and to make if the calculation from the molecular dynamics kind of match with mechanics? That would be super exciting for me. So to begin, we need to begin with the actual molecular simulation setup, and then we apply different models. So what's a simulation setup? We basically have a single layer of graphene in the simulation box, and the graphene has an initial defect, and the defect list can be tuned in the simulation, which is relatively simple, and we apply a thermal gradient to whether curious to see if the thermal gradient play a role in the fracture of graphene, and then we simply apply a swing rate to make the initial defect fracture happen and make the crack to propagate. And we just want to observe this phenomena to sort of benchmark question number 1, the effect of empirical potential. And what kind of empirical potential we use for graphene? So here we use optimized tensor potential, reactive bond order, which is Rebo, and adaptive interduplicate Rebo potential and Rebo M. And if you observe all these, those are not exact form, I have to say, are not exact form of the potential. It's just like pseudo equation for the audience to understand what I'm saying. Is for Rebo and tensor potential, they have similar form that contains attraction and repulsion, even though the exact mathematical formula are different. If you're curious, please come back to me later. I will show the mathematical formula. But for Rebo and tensor potential, they have attraction and repulsion term controlling the interaction between atoms, and they are multiplied by a cutoff function f, which controls or determines the break of the atoms and when the fracture happens. And for Rebo and tensor, they have similar form. What are a Rebo and Rebo M? Basically, a Rebo potential is you have this Rebo potential and add up a Lennard-Jones potential and with the Lennard-Jones potential and also the torsion potential. And for the Rebo M, it basically replaced the Lennard-Jones potential with the Morse potential, which calculated from ab initio or first principle calculations. So these are just general, give you an overview of the mathematical formula, and I hope you guys get the main point. And what I also remember, we apply a thermal gradient. So we just show you the temperature gradient along the graphene layer to kind of show how the temperature distribute after a certain step of simulation. And we get the stress strain response of the different graphene layer. So this figure, you can get a lot of information out of it. Different columns stand for different thermal gradient, and different rows stand for different empirical potentials, and different colors stand for different initial defect lists. So you can get a lot of information out of this figure. I won't dig too much into detail because for the sake of time, I only propose like extract two main information that I can observe from this figure. As first, we observe for Rebo potential, which is, this is a Rebo, I'm sorry, the font is too small, Rebo, a Rebo, and a Rebo M. And you observe for the black line of this Rebo base potential, black line stands for smaller initial defect, and then those color lines stand for a larger initial defect. And we kind of observe this like string hardening effect. And how do we explain this? Well, there's a lot of explanation based on my limited knowledge. First of all, you apply high strain rate loading, so it can be account for the string hardening, and also for only observed, because it only observed for smaller initial defect but not for larger one. So I will come back to this one later, so that's why I put a dagger there. Is when you have a smaller initial defect, the crack length relative to the crack width relative to the crack length cannot be ignored. So when you apply the loading, the morphology of the initial crack is kind of similar to a circular shape, rather than when you have a very long initial defect, this kind of just fracture happen on the crack tip. So when you have this circular morphology of the initial crack, this kind of crack edge shear the loading of the applied strain rate. And also we didn't observe a clear mechanism by compare different thermal gradient of at least I hope initially, but I didn't observe clear mechanism of the temperature gradient on the fracture, not temperature. Okay, then it goes to question number 2 is can we benchmark empirical machine learning potential? And what's the difference? So I'm just going to give you a very overview, like general overview of what's machine learning potential. There's a lot of machine learning potential proposed in recent years, but it all kind of goes back to this Biller and Cornell paper in 2007 of Pittsburgh letters. Of course, different, you can also use coordinate-based or graph-based, but a lot of people are using this symmetric function-based machine learning potential, which basically the key idea is they formulate this symmetric function G, which contains the rotation and angular part, and they input it in a neural network, and then output the energy of the interatomic interactions. And what we essentially use here is we use this machine learning potential in the reference as, so there's a lot of innovation point relative. It's kind of formulated based on this basic framework, but there's some innovation, but the two kind of give you the main general overview of this machine learning potential we use is basically to use the active learning strategy so that you can query for the initial calculation data to make the machine learning potential more accurate. The loss function contains not only the difference of the energy, it also contains the loss of the forces and the stresses. And also this machine learning potential is kind of based on this moment tensor potential, this kind of this tensor formula with very complicated mathematical formulation. And just give you overview, of course, please come back to me later if you're interested in the mathematical details. And so what do we get by benchmarking machine learning potential with empirical molecular dynamics potential in calculating the mechanical responses? So we get this figure, and you can get a lot of information out of it again, but only I will just briefly highlight the key part is those black line are the machine learning potential, and the color line is the empirical molecular dynamics potential, and you observe that the machine learning interatomic potentials underestimate the fracture stress compared to the empirical potential. If the fracture happened much earlier for the machine learning potential, and we observe the actual simulation of the crack propagation process, we kind of see that the crack they propagate is in a very brittle form, and after a certain strain, the machine learning potential implementation, the atoms scatter into or exploded into scattered atoms, which means the potential kind of failed to describe the post-fracture process or the physical process. And why? It's also very simple, because this potential is trained on short-range interaction from ab initio calculation. Of course, right now there are some researchers I know that are making effort in including dislocation or fracture in the ab initio data. So maybe you can do the simulation of actual fracture based on the machine learning potential, but based on our implementation, because the training data is from short-range interaction from the ab initio calculation, the machine learning potential cannot efficiently capture the fracture process and underestimate the fracture stress. And question number 3, can we verify molecular dynamics from mechanics? Okay, so another very general overview of the fracture mechanics is we use a framework called quantized fracture mechanics, sort of derived from the linear elastic fracture mechanics. And a general overview of fracture mechanics is a fracture stress and stress intensity factor is in this relation where this L is the initial crack length divided by 2. So you basically can think this as the initial crack length. And the quantized fracture mechanics is proposed by Cornell University. It's basically modifying linear elastic fracture mechanics by, of course, the actual, again, the mathematical formula, the actual implementation is much more complicated, but the key idea is elicit a characteristic length L naught, and this L naught includes the molecular size effect in the fracture process, modifying the linear elastic fracture mechanics. So what is L naught? I say the local effect. Let me give you a schematic to show what is exactly L naught. For graphene specifically, for our implementation, of course, for metal, L naught can be different. For graphene, if we have an initial defect like this is from the JP paper, you apply the loading. What is L naught here? Is L naught is the height of the hexagonal. So basically, linear elastic fracture mechanics assume the fracture propagates in a continuous form or perspective, and the quantists basically assume the fracture happened discretizely with a unit of L naught, and includes the molecular size effect in the quantized fracture mechanics fitting process. So what we get from fitting quantized fracture mechanics is our actual molecular dynamic simulation. This is the general figure of we get. So the black dashed line is quantized fracture mechanics derivation, or we derive from their form. And those dots are actual molecular dynamic simulation data. And based on fitting the quantized fracture mechanics with the molecular dynamic simulation, we can obtain the corresponding stress intensity factor KIC. And these 4 KIC are marked on the right top corner of the figure. And those KIC, surprisingly or not surprisingly, match pretty perfectly with experimental data from this Nature Communication paper. And the R square is larger, either much larger than 0.9 or very close to 0.9. So we're happy about it. We get a fitting from molecular dynamics with quantized fracture mechanics with very good accuracy, and also verified from the experiment. So that makes me exciting, right? But then let's use a final last figure to conclude this first part, or part number 1, which took a lot of time. So then I start to wonder, if you look at this figure and you forgot all the molecular dynamic simulation data, you just like, now you're pure mechanics people, and look at this black dash line. I started wondering, if you observe this black dash line, any of them, they all preserve the intrinsic relation. Is when you have a smaller initial defect, the fracture stress increases in a nonlinear form. And that drives the interest because, why is not in a linear relation, but why is a non-linearly increase of the fracture stress when you have a smaller initial defect of fracture, or we can call it pre-crack? So I started wondering, and I started thinking in the continuum mechanics or in a physical perspective, how do we understand this relation? How do we physically think, not mathematically, forget all the math. How do we physically propose and visualize understanding of this nonlinear increase of fracture stress? Well, obviously, I'm not smart enough to come up with the explanation from the mechanics perspective. Then I started to observe the pure molecular dynamic simulation data. And these 4 figures kind of tell you the same story. And if you, from this figure, can also observe it pretty clearly that if you hide this part, okay, and if you only observe these four data, you can still argue say I have a linear feed, right? But then we have a very small initial defect. The fracture stress really increases non-linearly. So then I'll start thinking, let's directly observe what's happening at this point. And then can we observe some explanation or propose some explanations, right? So let's directly observe this point. And then these four figures basically tell you we use different four empirical potential to observe the fracture stress. And that's why I put a dagger point at the very first slide on this project, or this part I'm going to come back to the dagger point. So if you observe this smaller initial defect, the fracture process, where the blue line initial stands for the initial moment, the red line, the red star, not the blue star, the blue triangle dot and the red star represent the moment of fracture happening. And this represent the moment before fracture happened and the moment after fracture happened. So these four sub-figures kind of tell you the same story. So let's zoom in a figure and see what exactly happening right here. So what's exactly happening in this figure is when you have this is the moment that before any crack happened. This is just a pure pre-crack or initial defect as it's shown right here. And this is the moment right before the fracture happened. And this is the dagger point I'm going to come back from the very first slide. As you observe the morphology of the initial defect, kind of similar to, you can argue is either a circular shape or a square-like shape. But anyway, it's not a very, so if you think from a very long pre-crack, the fracture just happened on the edge and the fracture is propagated. But if you observe this one, the morphology is kind of circular, of course. And then we propose that the forces on the crack edge along these two sides is sharing the loading when you apply the loading. And because it's sharing, it kind of lifts up the fracture stress. And that accounts for the observation that when you have a smaller defect, the fracture stress is a nonlinear increase form. And that's why I think this figure is beautiful to me personally, is what I am using molecular dynamic simulation, direct observation to explain something that I traditionally derived from mechanics. And that's very exciting. And I would like to use that to end my first part of the talk. And you might think, well, having you talk a lot about different theory, different molecular mechanics, that's very overwhelming, right? So I just want to give you a very simple review of what I talked in the last very long, lengthy first part. Is you have a forward problem with some X and with a model or map, and you get a corresponding Y. What I did in the first part is very simple. It's basically multi-scale modeling. So you have a scale alpha and scale beta. Alpha can be ab initio data, or if alpha is ab initio scale, or you can say quantum scale, then beta would be the molecular scale. And we kind of make the relationship or the connection between the scales. And if alpha is molecular scale, the beta is you can consider as mechanics scale. And if you break down this multi-scale modeling simple equation, you can see what we did is initially we do molecular dynamics. It's an XY map, and the map or the model is molecular dynamics. And we compare different empirical model in the molecular dynamics model or map, as we have optimized torso, Ribble, and a Ribble ebb. And we do density, or we use a proposed model, but you have density functional calculation of X2I map, and then string neural network can also be any regression model of the surrogate of the density functional theory calculation is the M, and you input the molecular coordinate or the general molecular formulation X, and you get a corresponding MD hat, which is a surrogate model of molecular dynamics. And this bracket is first question I asked, and this is the second question I asked. And what about the third question? It's fairly simple, as you have this XY map in QFM, which is quantum fracture mechanics, and you compare the Y. And so the three brackets represent the first, second, and third question. But you can just remember my first lengthy part, the talk as this very simple mathematical formula of connecting the scales. And I'll be a little bit faster from now on and talk about something that are more interesting and less theoretical, is we do anti-biofilm surface. So what are biofilm essentially? I write here is a global question, but it's actually not that serious, but it can be very serious. Is biofilm essentially is just bacterial cells accumulate on surface, and when they attach to the surface, they form a community and grow into a film. And when biofilm forms on any kind of surface, it's super hard to get rid of, and that's why it's so troublesome, because so many people trying to come up with methods to get rid of biofilm. right? So we want to, at least using our computational model, trying to solve this problem or this question. So I have a problem of application in marine technology, biomass, and biomedicine, and many different problems in many different fields. But essentially, if you look at from the mechanics perspective, why biofilm is troublesome is because the adhesion between the biofilm and the surface is very troublesome. So we want to reduce the adhesion between the biofilm and the subsurface. And in our proposed solution is we use computational models and Bayesian optimization, and we couple the two frameworks together and then propose some anti-microactive surface. At least that's our goal for this project. So again, similar to the graphene, we started asking some questions and we started to answer this question in part of research. So what question do we ask? Different from the graphene project is this whole biofilm part is we mainly focus on the second question. So the first question is how do we remove biofilm, and essentially is how do we simulate biofilm in computer, or how do we use computer models to model biofilm? And the second question is, now we have the computational model, and then we have optimization algorithm, and then how do we couple the two so that you can automate the design process digitally? And what's number three is what's the biomechanics behind optimization and design antimicrobial surface? Is after you generate some surface or some topology from the optimization, what's the biomechanical mechanism or physics? Can you explain why this kind of surface can help you remove biofilm? And that's question number three. But the whole project kind of focused on the second question, number two. And also similar to the graphene project, you have to initialize with a simulation framework. So our simulation framework is basically you have a subsurface and we parameterize the structure of the surface with a few design parameters or design variables. And you have the radius of the top and bottom of the cones and the height of the cones, and you can tune the number of the cones. Basically, you have 4 design variables that can perturb the structure of the subsurface. And you have a region that you can put bacteria on top of the surface, and you can let bacteria go in the computer simulation models. And if you're interested in the mathematical model, please ask me after I finish. And then now, this is the key part of the project is how do we automate the design process digitally, or how do we couple the design optimization? So if you're interested in theory or math, you can look at the equation, but I'm going to mainly explain our framework in this simple schematic. It's basically we initialize by Bayesian optimization, and the Bayesian optimization or BO gives you a set of design variables for design parameters, and its parameters control a specific active surface geometry. So after you obtain a geometry from this design variables in the computer simulation, then you put a set of bacteria distribution on top of the surface in the computer simulation and let the bacteria, initial bacteria, grow into a biofilm. And then after you have a biofilm, you apply a physical loading to remove the biofilm. It can be vibration, can be shear flow. And after removal, you have a simulation box that have a surface and remove biofilm. Then now in this simulation box, you cut the rest biomass or bacterial cell numbers and output to the Bayesian optimization as the objective that we want to minimize in the optimization framework. And then we can let this loop run again. After certain iterations, you might find some optimized active surface generated or extracted from the Bayesian optimization, and then you do verification and sort of explain the biomechanical mechanism of the removal process. And then this whole framework is achieved through a computational interface. We propose is we have some Python, the Bayesian optimization is implemented in Python, and the simulation is implemented in Labs. And we couple them together, passing the design variables and optimization, and it will give you the design in the actual implementation, the coding part. And what we kind of extract from the coupled digital optimization result is, so this is the surrogate model of the design space approximate Gaussian process from the Bayesian optimization. And those colored contours, or you can say contours, or those colors, represent the change of design variables normalized in the normalized sense. And this is the change of the objective, which is the residual bacterial number or residual biofilm in the optimization process. And you can extract those lower point or smaller bacteria number and then get their corresponding geometry. And then we get geometry based on different physical loading to remove biofilm. Which for pure growth, you get this kind of geometry of active surface. And for shear flow, you get this kind of geometry. And for vertical vibration and lateral vibration, you get this kind of geometry of the subsurface or subscript. And now it goes to question number 3. Is after we do the optimization, we get some active surface generated from the optimization. We need to try to explain some like mechanics under it. Why does this kind of surface can help us remove biofilm? And let's take shear flow as the most canonical example, because a lot of people, especially on the experimental side, they like to use shear flow to remove biofilm. So we do the comparison experiment between a flat surface and optimized surface, and then we let the biofilm grow into bacteria grow into biofilm and remove it. And you can see very clearly, specific for a shear flow example, the active surface is easy to remove biofilm, and the flat surface, the biofilm kind of adhere to the surface, and can also see from this figure that very clearly is effectively removing the biofilm through shear flow. So why? Now, if we do the simulation in this sense, compare active surface and flat surface, and go to biofilm, now you can count bacterial number in the z-axis or the perpendicular axis, and you can observe from these two lines where the blue line is the active surface and red dashed line is the flat surface. So for the flat surface, the bacteria or biofilm is more accumulate on closer to the surface. And for the blue line, which is the active surface, the bacterial accumulation or the biofilm generation is kind of lifted up by the syn pillar generated from the optimization. And there's a bacterial number accumulation reduction nearer to the surface. And we propose this reduction of the bacterial number accumulation is and reduce adhesion. And that's the key mechanism that can help us to remove biofilm in the syn pillar topology. And that's, we propose the biomechanics of removing biofilm in this framework. And we're happy about it. And then we answer the question, we generate optimization, and we kind of help also guide experimentalists and brought a lot of impact. So we publish paper and we put our code open source, and then we generate a lot of impact. So we're super happy about it. And that's my second part of the talk, of the biofilm part. All right. And then you might also think, well, there's a lot of different kind of fancy applications and figures, but then what's the key point of this biofilm project? I just want to remember, we understand this project through a very simple equation, just like you did for the graphene one. So now we have that. So a kind of review is for graphene one, we have multiscale coupling, or relationship between multiple scales is alpha and beta scale. Can explore the relationship. And for the biofilm one, if you look back for the forward problem, we want to remove biofilm, which we know the Y. And then we want to get a topology of the surface, which we are curious what is X. So we know Y and we want to get X. So essentially, if this is a forward model, then we have an inverse model. And you know the Y, you inversely get the X, and you tailor the structure of the topology. But there's a problem is, in our biofilm model, the map or the model M is a very complicated multi-phase, like biology. There's a lot of multi-scale coupling process that grows the biofilm and removal. Right? So that's not a very simple or ordinary differential equation, or it's not a simple linear map that you have a matrix and you can simply do the invert of matrix and get the corresponding X. So you can't directly do this inverse mapping. So how do we do that in the biofilm one? Well, that's a good question. And how do we do that? Essentially, we're doing design optimization that you have a goal of Y. So it's Y star. And Y star can be an exact Y, right? And Y star here is either maximize or minimize. So in the biofilm one, we want to minimize the residual bacterial number or bacterial cells. So you know the Y star, and you want to inversely get the X. So you are finding the argument of X to maximize Y, and to do this design optimization to kind of achieve the same scheme as the inverse problem. We're doing the inverse design optimization framework. But then if you look at this design optimization framework very closely or very clearly, we have this design optimization. And I want to add up a little part. So in the design optimization for the biofilm part is we initialize with a set of experiments, and you have some X and some corresponding Y, and we use it to train a surrogate model of the design space using Gaussian process regression. And then we use an acquisition function to query and search for the next set of X. And we let the loop run iteratively, which is a fancy schematic. I put it right there during the biofilm project, and we can kind of achieve this inverse map of Y star back to X star, and the X star stands for the geometry that you can remove out efficiently. But now it exists a problem again. Is design optimization we're focusing on is essentially this argument of finding an argument of X to maximize Y, where it can also be minimized in the same sense. But in the biofilm one, we're using Bayesian optimization. But Bayesian optimization is obviously not a single or only optimization method that you can use to minimize a specific objective. there's a lot of method they can use in this film project that you can bypass this direct mapping of inverse, but still achieve this goal, right? So there's a lot of method. And then I will go to my third part. And for the sake of time, my third part, the results are mostly still not published. So I will just only give you the framework and my thinking process, my thought of the third part, and only give you some very quick overview of the result, and then conclude the talk. So if you're a person in the, say, 100 years ago, if you're now living in 1923, and then you have a time machine and you travel to 2023, what will you be most amazed by? Oh, you might be amazed by the fancy cars and the chip, the nanotechnology, the batteries, the stretchable electronics, a laptop, where I'm using right now, or fancy drug design, material design, right? You have all those different fancy applications. But all those different kind of fancy applications are based on the fact that we have a lot of different materials that preserve a lot of different properties. And in the past, how do we do material design to get those corresponding devices for target materials? Is some smart guy that they know the corresponding structure property map of this kind of materials, and they do forward design and get a corresponding application. But as the whole world like progressing more like faster, and now we have ChatGPT and also like fancy AI tools, we are more in the era and we can imagine some application that we want, but we don't know the material we need to actually obtain the corresponding applications. So we can imagine we want something, we want this fancy laptop or like a giant iPad, right? That's kind of funny. But then we don't know what kind of material we need to build up the device we want. So the new kind of material design scheme is more like we inversely define materials of our need. And if you look at this kind of giant schematic, you might find something very similar that can trace back to the very first slide of my talk, which is you have some X and you get there's corresponding Y. And this is a forward mapping and this is an inverse mapping. And again, this project will be very fast. I will only give you the thought, my thinking process, the schematic way, the framework we come up with, and only highlight brief result. And then we began the research by asking question, how do we design molecular material digitally? This whole project is designing new molecular materials. But for biofilm one, I mentioned Bayesian optimization is not the only design optimization algorithm. So for this project, the key goal is how to benchmark different optimization methods, which is on question number 2. We kind of focus on this question, we have all those fancy optimization methods. And the third question is following up. Second question is what the extracted materials from the optimizations. And for a very fast, but I will focus on this schematic. So we come up with this design optimization framework for designing molecular materials. And if you're interested in math, you can also look at the equation, but I will mainly focus on the schematic that we benchmark reinforcement learning that use the agent to sort of explore the environment, which is a simulation or the structure property map of the materials. And we also benchmark Bayesian optimization as mentioned for the biofilm project, and also different meta-heuristic algorithm, including genetic algorithm, particle swarm optimization, simulated annealing, all like not all, but the most we can come up with and we can use at hand in Python implementation. And I want to mainly focus on this schematic of sub-figure A, and I want to zoom in to briefly elaborate what we propose to do the benchmarking of all those different design optimization algorithms. As you start from nothing, you don't like biofilm project, you start with a formulation of the substrate and tailor the parameters. This one, you start with nothing. You don't know anything, A per error. And then you assign atomic number and form a basis. So let me give you an example. If this number is 3, now you have a 3 as a basis. But what are these 3? We don't know. So now you only have the 3 as a basis. And your specific atomic type to the basis. And now you have a combination of atoms. It can be carbon, hydrogen, and oxygen, for example. And you have carbon, oxygen, and hydrogen. You can form a materials candidate library in this form. And then use a third design variables to find the corresponding materials among the library and get this corresponding molecular structure and input to a graph neural network, predict the property, and then do the optimization benchmarking. And this whole project is focused on how we benchmark different optimization in this framework under this benchmarking process. And I'm only gonna give you a very short elaborate on the result as we first do a single element materials and then multi-element. For the single element, this is we want to maximize the bulk modules and minimize the Fermi energy, and then we explore the design space, and those dots are exploration by all those different optimization algorithms. And this black dashed line is the property of silicon, which we define a constrained design space of silicon, and we count the number of different molecules exploring in a target design space bounded by silicon properties, and then we can count the materials count from all those different optimization algorithms, and then you can compare the result. But again, this is only preliminary result. We are keep updating this project. And then you can also visualize and reconstruct the design space for single element optimization, which is the map from the 2D variable to the bulk modules and Fermi energy. And you can also count the number explored in the whole optimization process in the constrained design space by combined by different optimization algorithms. And for a multi-element, you can do the same thing. You're exploring the kind of target design space, and then also count the number of materials explored in the target design space and compare the number counted by different optimization algorithms. And then you can also count all the different multi-element materials explored by different algorithms. And you can also calculate the mean objective among the exploration process and compare them. That's how you do the benchmarking. But again, this is pretty preliminary result. We are keep updating this project. Again, now it's a good time to do the conclusion and of the whole different three project. As we begin with something very simple. Go back to the first slide. Is you have some X and your corresponding Y, and do the map, and we define it as a forward problem. And based on this forward problem, we first do multi-scale modeling. They have a different computational model on different scales, ad hoc scales, alpha, beta. And based on computational modeling, we do inverse model. We can come up with the scheme of inverse problem, right? So you know the Y, and you get this corresponding X, and theoretically it's an inverse map, M inverse. But we don't know the exact form of the M inverse map. So what we do here, we do design optimization, and that's the second and third part of my talk. And do a short overview of the third part of my talk. As first, again, we do Bayesian optimization. You have a Gaussian process to approximate design space. As the target model, use acquisition function to query for next set of X, and you do the design optimization. And then we do deep reinforcement learning and use the deep neural network as an agent to explore the environment, which is the structural property map. And then you also do design optimization. And what we do is the third one is mathematical heuristic algorithm, which include genetic algorithm, particle square modulation, all those different heuristic methods. And then which we define as a rule R, and this R include the update of the particle locations and have the Y into the inverse mapping to achieve Y star map back to X star. And ultimately, we're just doing benchmarking that you have a Y star and you have an inverse model, which is target model M hat, and then get a corresponding X star. But among all those complicated equations, for the third project, you can just still remember it as a very simple formula that we do a benchmarking of the inverse design optimization. And that's a good time to conclude. Even though I use four very simple formula to conclude all my talk, I still hope to give you four very simple term or words to conclude my talk too. So what we began with is we began multi-scale mechanics. So we're kind of initially motivated by multi-scale mechanics that you have all those different computational models or mechanics models on different scales. And then what we do is we're looking at some different applications. Applications can be a graphene, can be a biofilm, can be molecular design. And then we do machine learning. That how can we use machine learning to kind of help us in multi-scale mechanics game, either do scale bridging, either do optimization, helping them use Gaussian process to kind of approximate the target model. And then eventually we do optimizations, and we're connecting all the four tools that we have in hand and to build up all those research. And eventually, I want to use the word that I initially motivated by as a single word that I began this talk with, is all those four kind of words is concluded by one single term, which is computations. And with that, that's basically the end of my talk today. And I think I'm pretty on time. And this is the course I took during my master's. And the main result come from the two publications and the presentation I presented my research. And after I graduate, I'm joining Stanford as a PhD in mechanical engineering. Oops. And with that, I'm officially stopping by now and taking questions from the audience. Oh, sorry. Okay. I don't know if anyone asking on Zoom or not. Okay.
Okay, so I can go first if no one else.
Yeah, okay.
So like in your first part, you show the figure of like different potentials that lead to different mechanical properties.
Yes.
Do you have a rough explanation, for example, why this kind of potential shows like a different result than the other kind of potential? For example, what kind of interaction is considered in this potential and that is not considered in the other one? Is there like a kind of relationship? Like maybe you go to not this thing.
The stress rate response?
Yes, yes.
That's a very good question. So
What kind of interactions, for example, is considering in one model, but it's not considering in the other model?
first question, I didn't look into details in the chemical part of the potential, where I'm only focused on the mechanical relationship and trying to explain the stress rate responses from a mechanical perspective. And that's a very good question to follow up, is look at how the chemical interaction in details tailor the interaction of the stress rate responses. But what I can tell you is in those all different empirical potentials, the attraction and repulsion term first of Riegel and Oppenheim is they all preserve exponential relation with R, which is the interatomic distance, but having very different form. So to answer your question as a follow-up work is how do we, because they all have the similar relation with the exponential term. So then the constant or parameter that multiplies the exponential term would be a key point to understand or explain from the chemical perspective why this we have this kind of stress responses. And the second is we look into this is compare a Riegel and the Riegel M is how do we explain the addition of Lennard-Jones and torsion part? How does they add up to explain the stress responses? But the first question is, I didn't thinking from the chemical, or at least in this project, I didn't explain from the chemical perspective for the stress responses.
Okay.
Yeah. Yeah.
How do you introduce noise into your biofilm project? And how do you prove it's robust?
Okay, that's that actually one of the reviewer asked the same questions, the same question. So if I understand your question correctly, the noise in my understanding is randomization in the generation of bacteria and growth of bacteria and then removal of bacteria. It's a randomization process. Like because it's simulation, how do we include the randomization effect? And at least that's one of the questions from the reviewer in this paper. And then our proposed answer is we have to make sure the bacteria are initialized in the same position, but also randomly initialized in the same position. That's why we are exactly looking at the effect of the topology of the substrate or the surface, right? So we show this, I think actually in the supplementary figures that we initialize the bacteria with the same random seed. That's why initially you have the same initial positions, but we are exploring the effect of subsurface. So we have an initial distribution of bacterial cells, but after it grows into biofilm, the total bacterial number changes, the position of bacterial number changes. Why does change is purely the effect of the subsurface. And that's what I understand is the effect of the randomization in the bacterial product. I don't know if that answered your questions, but yeah, you can keep following up. What was?
Yeah, and then what it changes, you apply a new random seed, but for a new I guess field of bacteria. Does that change your answer at all, or does it still remain?
So for the bench, that's why in the optimization, we want to make sure in the same optimization is the same random seed, right? But then you want to do the benchmarking or comparison to explain the biomechanical mechanism or biomechanical explanation of why does this kind of subsurface remove biofilm. That's why in the biomechanical comparison experiment, in this one is a different set of random seed. Okay. Yeah. And also these are just in the comparison of these totally different random seed or different randomizations. Yeah.
And just can you go back to 2018?
Yes.
Oh, the previous one. Yeah. So how does non-convective affect the design space? What's the I'm just for curiosity. So
That's one of the key part of this whole project is not designing like based on the finite element calculation. You can actually use gradient based optimization to design a structure that you are applying compression or loading from the mechanical perspective. Is in this project, because the design space is so non-convex, that's why we use a total randomized process to explore the design space. Is with you start from nothing. You start from like a mechanical design perspective. You know it's going to be a beam, and you want to design a topology of the beam. Is we start with nothing. That's why the total randomization process help us to account for the non-convex subsurface. That's why you can randomly explore a subsurface and extract the lower point. But the drawback of non-convex design space, the problem here would be you don't have a guarantee that the objective is strictly increasing or decreasing. That's why you're just like heuristically exploring design space and extracting the good point and then get the corresponding molecule. And the key goal is just to get the molecule that actually perform better. And that's the key goal. Yeah.